Okay, hi everybody. I am going to go through the solution for the finite potential well. To just talk about the problem statement a little bit, I'm going to plot the energy on the y-axis as a function of the position on the x-axis, and in the red line I have drawn in our potential energy. So in the region x less than 0, there is some potential energy u naught. In the region from x equals 0 to x equals L, there is no potential energy. In the region x greater than L, there is again potential u naught. Okay, and so we have some particle with some energy shown by this green line here, and the energy of that particle is less than u naught, meaning this particle should be contained within this well. Right? It doesn't have enough energy to get into this region at all, or get into this region at all. Okay, and as we always do in quantum mechanics, we are going to solve the Schrodinger equation given this potential. Okay, so I'm going to first split this up into three different regions. I'm going to call this region 1, I'll call this region 2, and I'll call this region 3. Okay, and basically we want to solve the Schrodinger equation in each of these regions, and then we're going to apply boundary conditions to make sure that they match, that we have a continuous wave function in between the regions. Okay, and I'm actually going to start with region 2 because that's something that's most simple because there's no potential energy in that region. So in region 2, right, this is the region 0 less than x less than L, and in that region we have the potential energy equal to 0. Okay, so in order to solve the Schrodinger equation in this region, first we write down the Schrodinger equation. Right, this is the time-independent Schrodinger equation, and I can ignore the potential energy term because the potential energy is 0, so the Schrodinger equation is relatively simple. I'm just going to rewrite this, solve it for the second derivative term here. Okay, and we'll just simplify it a little bit more, just because we've seen this grouping of constants before. You may remember this equation that we've already introduced. We can write the energy in terms of h bar squared, our wave number squared, divided by 2 times the mass. And we can note that here we have 2me over h bar, and if I rearrange this, I also have 2me over h bar squared, excuse me. So basically I can solve this for k squared, and that's equivalent to 2me over h bar squared. So I can just replace all these constants with a k squared, and I'll just make life a little bit more simple. Okay, so here's our differential equation, and we need to solve this, and we're basically going to guess an answer, and because we've seen this type of equation before, we need some function, right, some wave function, where if I take two derivatives of it, I get the same function back, just with some minus sign out in front and some constants out in front. And we know from experience that cosine and sine satisfy that differential equation. Right? If you take two derivatives of cosine, right, you take one, you get negative sine, take another, you get negative cosine. You get the same equation back, but with a negative sign out in front. Okay, so, and since cosine and sine are both solutions, we are actually going to write the linear combination of these as being our solution. So we are going to just say that the wave function that satisfies this differential equation is a sine of kx plus b cosine of kx. Alright, so we don't know what these constants are yet, and but we know it could be some linear combination of sine and cosine, and you can check, you can plug this wave function into this equation. I take two derivatives of this, I should get minus k squared times my original wave function. Okay, so we're going to leave that for now, we'll come back to that, and let's move on to solving the Schrodinger equation in region 1. Okay, so we've already solved the Schrodinger equation in region 2, and we found that in this region where there is no potential that we got sine and cosine solutions. Now let's try to solve the Schrodinger equation in region 1, where now we have some potential energy. Okay, so region 1 is the region x less than 0, and so to do this we again need to write down the Schrodinger equation, And this time we need to include the term that includes the potential. Okay, so there's our time-independent Schrödinger equation. And again, to solve this, let's again solve for our second derivative. And I'm just going to move this u-naught term over to this side and then move these constants over, and such that I find this. Okay, so I've basically just rewritten my Schrödinger equation now. And again, I have a bunch of constants here. Let's just give those a name to help us keep track of them. I'm going to call that all alpha squared. So I'm going to define alpha squared to be equal to 2m u-naught minus e over h bar squared. Okay, or alpha is just equal to the square root of all of this. Okay, so when I do that, again, we get a nice simple looking equation. Okay, so there's the differential equation now. And so we need to look for a wave function that satisfies this equation. And we can note that, again, looking at our picture, E is less than u-naught. The energy of our particle is definitely less than u-naught. So energy is less than u-naught. So whatever's under the square root is definitely some positive, and so alpha is just a positive real number. Okay. Alpha is positive and real. Okay, so alpha squared is positive and real, and therefore we need to find a wave function where if I take two derivatives of it, I get the same function back, just with some constant popping out. Okay, and again, cosines and sines are not going to work in this region, right? Because if I used a cosine or sine, I'd get a minus sign popping out when I took two derivatives. But you may guess that an exponential may be a good solution. Right? With an exponential, if I take a derivative, I get the same function back. If I take another derivative, I get the same function back, and every time an alpha will pop out. Right? So that's going to be our guess. And again, it could either be e to the alpha x or e to the minus alpha x, so we're going to do a linear combination of those two options. Okay, and so that's a constant d there. That's my guess for the wave function, and you can check on your own that I could plug this wave function in here, take two derivatives, and I should get alpha squared times my original wave function. All right, so that's our solution. But now let's think critically about these two terms. I've got one term which is e to the plus alpha x, and one term which is e to the minus alpha x. And if I look at my picture, I'm in region 1, so I'm at some negative x position, and I can think about if I have a particle which is bound within this well, what is the probability as I go to minus infinity of that particle still being there? And that should go to 0, right? It shouldn't go to infinity. Right, so we can think about that as x goes to minus infinity, we want the probability, or psi star psi, to go to 0. Okay, and we're in some negative position. So if this is negative x, e to the minus alpha times the negative x, this is e to some positive, and so this is going to get bigger and bigger and bigger as I go to minus infinity. So this term definitely isn't going to be able to describe this particle in this region. Okay, so I can recognize that I can just kind of cross that out, and the wave function in region 1, and maybe I should label it like that way, the wave function in region 1 must be just equal to c e to the alpha x. Okay, and now let's think about region 3. Okay, it's basically going to be the same Schrödinger equation and the same solution over here. We're just going to have to make a separate argument as we go to positive infinity that the wave function should go to 0. Okay, so let's do that real quick. In region 3, right, and so that's the region x greater than L. Right, we also have a potential in that region. I again write down the Schrödinger equation, I again solve it, and I'm going to get basically the same thing I had up here. And I'm going to again guess that the wave function in that region is some sum of exponentials I'm just going to pick different constants here. And now let's make the same argument. As x goes to infinity, we want the wave function, and therefore the wave function probability, to go to 0. Okay. And looking at these, as x goes to infinity, this term's going to get really big, so it can't be this. This term must be a good solution. Right? So I'm going to cross that out. And so in this region, the wave function in region 3 is equal to g e to the minus alpha x. Okay, so we've now solved for the wave function in each of these 3 different regions. Okay, and let me get a new piece of paper out here and rewrite these for you. Okay, so what we found is that in region 1, and this is x less than 0, make a little table here. The wave function we found is equal to c e to the alpha x. In region 2, which is the region from 0 to L, the wave function we found in that region was equal to a sine of kx plus b cosine of kx. And in region 3, which is x greater than L, we found the wave function to be equal to g e to the minus alpha x. Okay, and we'll note right away that inside the well, the wave function is sinusoidal. And outside of the well, we have decaying exponentials. So let's just recognize that we get different answers in different regions, and that's interesting. And in order to fully solve this, in order to figure out what all these constants are, and find out what the possible energies this particle could have, and find out, do we have quantized energy like we found in the infinite square well or not, we need to apply boundary conditions. Okay, so let's do so. So in terms of the boundary conditions, the first rule is that a wave function has to be continuous. And so at the boundary, the wave function has to be continuous. So what does that mean? Let me draw a few pictures. That means that inside the well, we're going to have solutions that are some type of, sinusoidal function. So it could be, something like this. Okay, inside the well, we get some kind of a oscillating solution. Outside the well, we have decaying exponentials, right? But there's certain solutions that just aren't going to work, right? If the wave function in this region is this decaying exponential and in this region is this decaying exponential, I can't have these big jumps, right? At the boundary, the wave function has to be continuous. That is, at the boundary, and this is region 1, this is region 2, this is region 3. At the boundary, this is x equals 0, this is x equals L. At the boundary, at x equals 0, the wave function on one side of the boundary has to be equal to the wave function on the other side of the boundary. Okay, and that also has to be true over here. Okay, so I think that makes sense. So this is going to lead right away to some energy quantization, right? You can imagine that as I try out different wavelengths in here, there's only certain ones that are going to match my decaying exponentials. Okay, and we can kind of look at the k in our sinusoidal functions and see that the k depends on energy. So as energy increases, my wave number is increasing. And if you recall our definition of wave number, as my energy is increasing, my wavelength is decreasing. So as I increase in energy, I'm decreasing my wavelengths, I'm fitting more and more peaks and troughs into the well, but only certain versions of that wave, certain wavelengths are going to fit such that it meets this boundary condition. Okay, so we just mark this is not what we want. This does not work, and so what we want to happen at the boundary again is that we have something like this, where at the boundary we have a nice decaying exponential, and it matches. Okay, so this is what we want. Okay, so that's the first boundary condition. The second boundary condition is that the wave function has to be smooth at the boundary. Wave function smooth at boundary. Okay, so what does that mean? That means, again, let's draw our potential, and this is x equals 0, this is x equals L. Smooth at the boundary means that even if I have a nice sinusoidal function inside and a nice decaying exponential outside, I'm not the best artist in the world, but as I drew it here, you can see I've got my first boundary condition is satisfied, where the decaying exponential has the same value at the boundary as my sinusoidal function, but the way I drew it, the slope is a little bit different, right? There's a kink here and there's a kink here, and we can't have that. Okay, if we had a kink here, okay, a kink, right, means that the second derivative is going to be infinite. And what that would mean, again, if I wrote down my Schrödinger equation, this is the rearranged version we had earlier. Right? If this is infinite, that would mean our wave function is infinite. That doesn't make sense. This is some finite constant here. Just doesn't make sense. All right? So we can't have any kinks at the boundary. So the mathematical way of saying that is that the derivative, the first derivative of our wave function, or the slope of our wave function at the boundary, has to be equal to the slope of the wave function on the other side of the boundary. All right, so at x equals 0, the wave function slope in this region has to have the same slope as in this region. Right? We have to have the same slope here. We can't have two different slopes like that. Okay, and the same thing at x equals L, the wave function in the middle of the well, x equals L, has to be equal to the slope of the wave function outside the well. Okay, in that region. All right, so what we want to happen is we want, and again, let's check my art skills here, we want to have a nice, sinusoidal type wave function, and then at the boundary it's a nice continuous wave function with the same slope on either side of the boundary. Okay, so I don't know if my art skills really pulled it off, but that's what we're looking for. So okay, now we have these two boundary conditions, or I guess, and we have, let me see, where was my previous piece of paper? We have all these different regions, so we basically have to figure out what these constants are by applying these boundary conditions. So let's do that. Okay, so here are three regions, and our first boundary condition was that the wave function in region 1 at that boundary at x equals 0 has to be equal to the wave function inside the well in region 2 at that boundary. All right, so this, I plug in my wave function, c e to the alpha 0 is equal to, plug in my wave function 2, a sine of k times 0 plus b cosine of k times 0. Okay, and sine of 0 is equal to 0, so that term is just equal to 0. Cosine of 0 is equal to 1. E to the 0 is equal to 1, so that just means c is equal to b. Okay, so we already figured out something about the constants. Let's apply one of our other boundary conditions. At x equals 0, the slope of the wave function has to be the same on either side. Okay, and so let's take a derivative and plug it in here. For region 1, I take a derivative, I get alpha c e to the alpha x, and I plug in x equals 0, and that has to be equal to my derivative of my sinusoidal wave function. So when I take the derivative of sine, I get cosine, so I have plus a cosine, ak cosine, k times 0, minus b k, derivative of cosine is negative sine, sine k times 0. So okay, this term is again equal to 0, this term is equal to 1, right? This is equal to 1. Oops. And so that means that I have alpha c must be equal to a times k. And so that means that a is equal to alpha c over k. Alright, so that could be helpful later. I'll write down, I'll circle all the important things we're finding here. Okay, what else do we know? At the other boundary, we know the wave function must be continuous. Okay, so plugging in, region 2 is again our sinusoidal. So I plug in x equals L. And in region 3 we have our decaying exponential. Okay, so that's doesn't tell us much yet, but we'll see how we can use this later. In fact, I already have shown that b is just equal to c, and a is equal to alpha c over k. So I could get rid of a and b in this equation and just replace them with c, with these two things I found already. So when I do that, I replace a with this, alpha c over k, sine of k L, plus b is equal to c, cosine of kl must be equal to g e to the minus alpha L. Okay? And so that's useful. We'll see where that takes us. And then let's write down our last boundary condition. Okay, our last boundary condition is that the wave function must be smooth at x equals L, or that is that the slope must be the same on either side of the boundary. Okay, so when I plug in, again this is our sinusoidal wave function, I get derivative of sine is cosine, and derivative of cosine is minus sine. And over here I'm going to take a derivative of our exponential wave function, our decaying exponential. I get minus alpha g e to the minus alpha L. Okay, and once again I can get rid of a and b in this equation because I know that a is equal to alpha c over k, and I know b is equal to c. Okay, and I'm just going to divide both sides by minus alpha. Let me cross out both of these k's, and I'm going to divide both sides by minus alpha just to take this one more step. Right, so this one becomes minus c cosine of kl here this becomes plus k over alpha. Oh, I'm sorry, I was supposed to replace this b with a c. Sorry about that. And c sine of kl, and this becomes equal to g e to the minus alpha l. Okay, so with the four boundary conditions, I've come up with a bunch of equations. C is equal to b, a is equal to alpha c over k. I use these two things to simplify our other two equations. So I have this one that just depends on c and g, and now I just derived this one which just depends on c and g. Okay, and I'll note that the right side of both of these is the same. Right, so that means I can set this equal to this. Okay, and so let's do that. That means that alpha c over k sine of kl plus c cosine of kl must be equal to minus c cosine of kl plus k over alpha c sine of kl. Okay, and so now I have an equation that just depends on one constant, right? There's no g in there anymore. And in fact, the c's all cancel, so I've gotten rid of all my constants, and now I have this equation which I can simplify. And remember, k depends on energy, alpha depends on energy, so we've got energy and wavelengths and the wave number in here and things like that. So let's see where this takes us. Okay, and we'll have to do a little bit of more manipulation here. If I divide everything by sine, I get alpha over k plus cosine kl divided by sine kl is cotangent kl. On this side, cosine divided by sine is minus cotangent kl. And here I divide by sine and I get just plus k over alpha. And now let's simplify a little bit more. I end up with 2 cotangent of kl is equal to k over alpha minus alpha over k. Okay, so there's my solution. Right? Not pretty, but we do have a solution here. And remember, k is equal to 2me over h bar squared, and alpha is equal to the square root of 2m u naught minus e over h bar squared. So when I plug in k here, k here, k here, plug in alpha here, I have this big ugly equation that depends on energy. And it may not be obvious looking at it, but it turns out this does imply that energy is quantized. Okay, how do we know that? Well, unfortunately, this is a transcendental equation, which means I can't solve this anymore with a pen and paper. But we can plug it into a computer, or you can plot it, and you can figure out which values of energy satisfy this equation. And when you do that, you get energy quantization. Right? You get only certain energy levels are allowed. Right? So for a given well depth, U naught, right? Only certain energies satisfy. Okay, so if I fix, remember in alpha we have U naught, so if I fix U naught to be some certain value, we then find that only certain values of E, which are found in K and alpha and these constants here, only certain values of E satisfy this equation. So that is energy quantization. Only certain energies and correspondingly certain wavelengths will satisfy. Okay, so what else does this tell us? A lot of interesting things. So first, let's just take the most obvious. Well, let's think about our wave functions a little bit. First of all, our wave function is extending into kind of the classically forbidden region. Right? So it turns out that we got a sine or cosine in the if I draw on the different energy levels, we get some kind of a sine or cosine solution for the first energy level inside the well, and outside the well we have this kind of decaying exponential. And the next energy level will be, oops, my art skills here, something like this. Sorry, my art skills. It'll be a lot easier for me to actually draw. Let me draw the wave function squared. That'll be a little bit easier for me to draw. Okay, so if I draw the actual probability of finding the particle, let's try this again. So inside the well we get some kind of a cosine or sine solution. Outside of the well we get some kind of a decaying exponential. For the next energy level we get some kind of a wave function like that. Okay, for the next energy level we get some kind of wave function like that, and I'm sorry, some kind of probability like that, wave function squared. And you'll see that again, if I look at these different energy states, there's some potential that we find the particle inside the well, but there's some potential we'll find the particle outside the well. So that's one of these amazing things we'll notice about quantum mechanics, that the wave function extends into classically forbidden region. Okay, and we can actually try to quantify that a little bit. We know that our wave function outside the well is proportional to e to the minus alpha x. Okay, and so we can kind of note that when this quantity, when alpha x is equal to 1, the wave function, the exponential decays by one over e, right? E to the minus 1 or 1 over e, right? Which is somewhere around a third, throughout 0.367. And this is kind of a classic way of quantifying how far something penetrates, right? So the wave function decays by 1 over e when it travels in a distance of alpha times x. Okay, so I can solve for x, right, and I'm going to just give that a name. That distance where the exponential decays by 1 over e, I'm going to define to be the penetration depth. And we often give that the symbol delta. Okay, so that's a way of quantifying how far this object penetrates. And when I solve for delta, delta is equal to 1 over alpha, which is equal to h bar squared over so h bar over 2m u naught minus e, and that's all square rooted. So h bar squared. Yep. And I note that as energy gets closer to u naught, right, as my energy increases, my energy is less than u naught, but as my energy gets closer to u naught, this gets smaller, it's in the denominator, so my penetration depth gets bigger. Right? So as I go to higher energy levels, as my energy gets closer to u naught, the penetration depth gets bigger. Okay, so that's another interesting thing, and I kind of drew that here a little bit, that as I increase in energy, the actual depth of that this wave function is penetrating into the forbidden region is increasing. Right? So that's one more interesting thing about the square well. It's a bit of a tough solution because we get a transcendental equation, but I think the consequences and the results are really interesting, so I wanted to go through the full problem. So, thank you.